So when we throw an object, like suppose this marker, if I throw it up, it will ultimately go to a height and come back, right? Why? That is because of the gravitational pull of the planet. Right now it's Earth. So what is the escape velocity? If I throw it with all of my velocity, all of my force and power, where will it go? Again it will go to, no doubt it will reach a bit more higher this height, but again it has to come back because of the gravitational pull. So is there any velocity possible with which, if this body is thrown vertically upwards, it will overcome the gravitational pull of the planet or the gravitational pull of Earth? That velocity is called escape velocity. So in definition, this is what it is: the minimum velocity which is required by the body to escape the gravitational pull of Earth or gravitational pull of a planet. Now suppose Earth to be perfect spherical of radius r, right? We are projecting a body of mass small m. See, what we just said was, in definition, that escape velocity required by a body is the velocity with which, if it is projected, it escapes the gravitational pull of a planet. Now, according to gravitational field theory, gravitational field extends up to infinity. So apparently this velocity is taken to be that velocity with which it starts or with which it is projected from the surface of that planet, right? So now we are not going to use the word planet, we are going to use the word Earth only, because we are doing this all in respect to Earth. So consider that this body, okay, before I start it, I'll tell you how we are going to find the expression or the value for escape velocity. The theme here is, I'm going to find out the work done in taking a small body of mass m from the surface to infinity, and once work has been calculated, I'll equate it with the kinetic energy using work energy theorem, that work done is equivalent to kinetic energy. This is the theme. So right now we have this body of mass m, it has to be projected vertically upward, so we are giving it some velocity which is escape velocity Ve, with which it is projected, right? And this is what we have to figure out, this escape velocity. Right now let's consider that this body is at height x from where? From the surface, because radius r has already been taken into account. This is distance x, and let a small amount of work is done in moving this body further up dx. Okay, so right now the force acting on it is, first of all, suppose the body is at distance x, so force acting on the body is g m, the mass of this planet be m, or Earth, mass of this body be small m, g mm upon the distance at which it is, this body is in with this body, is g mm over x square. For large distances you can take the value to be, see, we ignore the value of radius for large distances, but right now we have to take it into account, reason being x and r are still comparable, right? So this is the force acting on the body, g mm upon x square. Okay, if you are still thinking that if the distances are calculated, suppose the bodies, the mean mass of the body is concentrated at the center, that is what I'm talking about is center of mass, and the distance of mass m and capital M would be r plus x. No, we will not, reason being we have to do it from the surface of Earth. This is where we project the body, right? We don't project the body from the center of Earth, we have to do it from the surface of Earth. Also, when the body is gone, it has gone beyond the gravitational pull of the planet, then that distance is very large as compared to the radius of Earth, so this distance is negligible. That is why we are going to do it in this way only. Now this is the force acting on the body. We have to figure out, let dW be small work done in moving the body by small distance dx. So in that case, small work done would be f dx. So we can calculate the total work done in taking the body from this surface to the infinite distance, right? So how we can do that? Therefore total work done would be integration dw from, where are we taking it from? Radius of Earth to infinity. Okay, put the values respective, what dw f dx, and instead of f dx I can take, where is f, this g mm over x square r to infinity g m over x square dx. So I have this work done is equal to this gmm can be taken out of the integration, and I'll be left with dx over x square from r to infinity. 1 upon x square is what? X raised to the power minus 2 dx. So this thing can be written as gmm r to infinity x raised to power minus 2 dx. And if I use that formula, what? X raised to power n integration is n times x raised to power n minus 1. So I'll be left with gmm n times, that is n times x raised to power minus did I say the right formula for integration? Obviously not. The formula I just said was for differentiation, not for integration. What is the formula for integration? X raised to power n plus 1 upon n plus 1, right? So this will become x raised to power minus 2 plus 1 upon minus 2 plus 1. So we have, where is r and where is infinity? The limits from r to infinity. This becomes x raised to power minus 1, which can be written as 1 upon x, and this becomes minus 1, which is taken outside. Putting the limits infinity and r, how do we solve it? Upper limit minus lower limit, 1 upon infinity minus 1 upon r. Upper limit minus lower limit. So after doing this, 1 upon infinity is 0. I'll be left with this whole thing multiplied by minus 1 upon r, right? So this whole thing will become positive, and therefore the total work would be g capital M small m upon r. This is the total work done in taking this body from the surface of earth to infinite distance. Okay, now how do we solve it further? If V naught, which I initially wrote and rubbed up, if VE, not V naught, VE is the escape velocity which we have to figure out, or it is that velocity with which the body has been projected. So according to work energy theorem, whatever kinetic energy was there in the body, that got converted into work done by the body. So basically what we are using, the work energy theorem. So what we are going to start it and how we are going to frame it is like simple. Kinetic energy associated with the body is what? Half mve square, and then according to work energy theory, kinetic energy would be equal to work done by the body. So half mve square. I'll repeat that sentence. Kinetic energy associated with the body is equal to work done by the body. Okay, this is equal to, what is the formula we have? Work done is gmm over r. Gmm over r. So what we get now? This cancels out, and we are left with 2 gets multiplied here. Ve square is equal to 2gm over r, or Ve is equal to under root 2gm upon r. So this is the formula for escape velocity. Now you must be just relating it with orbital velocity. The formula was under root gm over r, right? There wasn't any 2 there, and in escape velocity there is a 2 here. So this is the required expression for escape velocity, which is the velocity required by a body to escape the gravitational pull of a planet.